Check. Can everyone hear me? Does it work?
Good morning, everyone, and welcome to this morning session on cryptographic protocols. We have 4 talks. The first one is called Universal Composition with Responsive Environments by Jan Kamenich, Robert Anderlein, Stephen Crane, Ralph Kusters, and Daniel Roche, who is giving the talk.
Thank you very much for the introduction. Today I'm happy to present you our work on universal composition with responsive environments. And I want to start my talk with a very brief recap of universal composability models, so everyone here is on the same page. Universal composability models use simulatability to define security, which essentially works as follows. We have some real protocol P, which we want to analyze, and we have an ideal protocol or ideal functionality, which perfectly defines some task in a secure way. For example, we might have an ideal functionality for key exchanges. Now, P realizes this functionality, or P is secure, if for all possible adversaries that try to attack P on the network, we can find an ideal adversary or simulator that attacks F on the network, such that no environment can distinguish both settings. Or in other words, it does not matter whether we attack P on the network, we might as well attack F instead and get the same kind of information. Main feature of these models is their modularity, which allows for reusing security results. This works roughly as follows. Let's suppose we have already shown that some real protocol P realizes an ideal functionality F. For example, we have already shown that we have a key exchange protocol. We might now want to build another protocol, Q, which serves a different purpose. Say, for example, we might now want to build a secure channel protocol. And this protocol Q can reuse the ideal functionality F for this purpose to show that it is possible to realize a secure channel. Once we have shown this, we can use the composition theorems from these frameworks to automatically conclude that even if we replace F with its realization P, the resulting protocol will still be a secure channel. Of course, we can iterate this. For example, we can now build a protocol on top of F prime, which uses the secure channel. And once we are done with analyzing this protocol, we can replace F prime with its realization Q and P. There are lots of different models that use this approach. However, our work is model independent. We have exemplified this by applying it to these 3 major models. So what exactly is the problem that we addressed with our work? In the following, I'm going to explain what urgent requests are and why they cause what we call the non-responsiveness problem. And then I'm showing how we solve this problem entirely by proposing responsive environments. So when we model a protocol in universal composability models, we often have to exchange some purely modeling related meta information with the adversary. There are several possible examples for this. Protocols often ask the adversary to provide a corruption status for the protocol to model that the protocol is secure both when running in an honest environment and both when running with corrupted protocol participants. Many protocols also allow the adversary to choose or provide some cryptographic material. For example, this is often done by ideal protocols, which might ask the adversary to provide some keys to model that they are secure even in a setting where the key distribution is arbitrary. Sometimes we want to leak information to the adversary, for example, to model honest but curious corruption. In this case, the adversary gets to see the entire internal state of a protocol without being able to influence the actual protocol run. And sometimes it's necessary to signal that some event occurred. For example, we might want to tell the adversary that a new protocol instance was created. All of this is easily done by just sending a simple message over the network to the adversary, and these messages are what we call urgent requests. Urgent requests have one important property, namely they do not model any real network traffic. If we were to look at an implementation of this protocol P in reality, this message would simply not exist. A real protocol does not ask, am I corrupted on the network? It also does not ask the network to provide some algorithms to use. So instead, the protocol run would continue without giving a real adversary any way to interfere with this protocol run. So if we go back to our security model, it would be natural to require the same from our adversary in the security model. He should also allow the protocol to continue its run without interfering in any way by simply providing the expected answer. The adversary should just tell, for example, whether the protocol is corrupted or not. It should just provide the keys that it was asked for. It should just return control if, for example, the protocol signaled that some event occurred. While this is quite natural, this is actually not the case in any of the current universal composability models. Instead, our adversary in these models is actually much more powerful than any real adversary, as he can abuse these urgent requests to mount distinguishing attacks. For example, the adversary might choose to activate the protocol in an unexpected way instead of answering an urgent request. So this might look as follows. Once he receives the urgent request, he sends a message to the environment, and the environment in turn can now send some I/O input to the protocol, which the protocol might not even be able to process as it is still waiting for a response from the adversary. The adversary could also try and change the state of other parts of the protocol in between, which might look as follows. Here we have a protocol P, which has a subroutine F, and the adversary is free to interact with F in arbitrary ways before it returns control to the protocol P. So every real protocol has to keep this in mind, that other parts of the protocol stack might have changed the state before receiving a response. And even worse, there are even cases where the adversary can block parts of a protocol entirely. For example, if the subroutine needs some algorithms to perform its task, it might ask the adversary for these algorithms, and by simply never providing the expected algorithms, we now have a situation where F cannot do anything anymore. It's effectively blocked. If the adversary now activates P instead, P has to deal with a blocked subroutine. Altogether, we are in a situation where protocol designers have to deal with a lot of unintended adversarial behavior, which importantly does not relate to any attacks in reality. Dealing with this is quite difficult. In some cases, it might not be possible at all. And if it's possible, it complicates protocol specifications and proofs quite a lot. Also, because it's so very unnatural to think about these artificial attacks that do not relate to anything in reality, it's often forgotten in the literature, which in turn leads to underspecified protocols, flawed security proofs where the composition theorem can no longer be used, and functionalities that cannot be reused to build new protocols on top of it. This was quite theoretical. I want to illustrate the use of urgent requests in practice by showing you some examples from the literature and showing you what exactly can go wrong. So in the following examples, it's not so important to understand every detail of these functionalities. I've highlighted the sections where urgent requests occur, so please look at the highlighted parts. Here we have an ideal functionality for non-interactive key exchanges. And this functionality, in case one of the participants is corrupted, sends an init request to the adversary and expects a session key in response. This is a very natural system. If the session is corrupted, then the adversary should be able to choose the session key of the key exchange. However, by using this system, we actually end up in a situation where fnike no longer is non-interactive. The adversary gets activated, so a higher level protocol that has just called this functionality to provide a key now has to deal with activations by the adversary. Even the authors acknowledge that this is quite unsatisfying, but at the same time, it's really the best one can do in current models if we want to allow the adversary to choose the session key. Here's another example, an ideal functionality for signatures of knowledge. This functionality has a setup phase where it sends a setup request to the adversary and expects to receive several algorithms in return. However, the adversary is of course free to never provide these algorithms, in which case the functionality has to operate on undefined algorithms, which can lead to problems if we want to reuse this functionality in another realization. We might end up with a distinguishing attack based on this. This is an ideal functionality for certificates, and this functionality contacts the adversary to verify certificates. It expects some value in response, which is then used in case the signer of the certificate is corrupted. So essentially, once the signer is corrupted, the adversary may choose freely whether a certificate is accepted or not. However, by activating the adversary is free to quickly corrupt an honest signer before returning control, which in turn allows an adversary to accept invalid signatures even though they should have been rejected. The authors also provide a realization of this functionality, which is a nice example to illustrate two other aspects of the non-responsiveness problem. This realization uses an ideal subroutine called fsic to sign messages, and of course it expects an immediate response from this subroutine. Signing is some local operation, so it should just return the signature immediately. However, this is actually not the case. fsic uses urgent requests for signing messages, so once it receives the sign request, the adversary gains control and is now free to mount one of these distinguishing attacks on the protocol. This illustrates that the problem propagates throughout the whole protocol stack. If there's at least one subroutine using urgent requests, then all higher level protocols have to deal with unintended adversarial behavior. They have to specify in particular what happens if they send a message to a subroutine, are still waiting for a response, and for example, receive some message on the network or on the I/O interface in between. Sadly, this is not done in this realization. As you can see here, this realization simply assumes that it immediately receives a signature from the subroutine. It does not state what happens, for example, if it now receives a message on the network instead. I can illustrate another aspect of the problem using this example. Suppose for a moment that we did not build this realization using the ideal functionality fsic, but instead try to build it directly on the realization of fsic called psic. Of course, this goes against the spirit of universal composability models. We want to use ideal functionalities to simplify our analysis. They are conceptually very simple. And then we want to get the replacement with their realization for free using the composition theorem. However, if we had defined the whole realization like this, then P would actually be well defined, because psic indeed immediately answers signing requests. There are no urgent requests involved anymore, so P does not have to deal with any activations by the adversary or environment in between. Altogether, we have a situation here that shows that idealizations cannot express certain properties that might be present in realizations. We could end up in a situation where we can prove a protocol secure using a realization, but we cannot prove it secure if we had used an ideal subroutine instead, which is really undesirable and goes against the whole spirit of the universal composability frameworks, which try to replace parts of a protocol iteratively with ideal functionalities. So, as we have seen in these examples, it's very important that protocol designers specify what happens if a protocol is still waiting for a response from the adversary or subroutine, but receives a message on the network from the adversary or an unexpected message on the I/O interface instead. There are several possible workarounds that one can try to apply to get a full specification for these cases. Perhaps the most intuitive one is just to say, I'm still waiting for an important response, so I will drop all other messages that I receive, I will just block them. Alternatively, we might also be so nice and just return an error message that tells other protocol parts that we're still waiting for some response from the adversary. Maybe we could try to queue new requests and process them later on once the adversary was so nice to answer our urgent request. We could also try to reduce the use of urgent requests by using code upload constructs. Or in some cases it is possible to resort to a default. For example, if we wanted to receive some algorithms from the adversary and the adversary does not provide these algorithms in time, then we could use a default algorithm. However, we have shown in our paper that none of these workarounds is generally applicable. Instead, protocol designers always have to craft solutions that are specifically tailored to both the realization and idealization they are currently analyzing. And in any case, these solutions just unnecessarily complicate both the protocol specification and in turn also the security proofs. Furthermore, even if we have gotten a full specification, we still have to deal with the unintended state changes, which in case of the ideal certification functionality led to a situation where it accepts invalid signatures or certificates, and the limited expressivity of UC models. So how did we solve this mess? We proposed responsive environments and responsive adversaries which essentially behave just as one would expect. So in our framework, a protocol can specify that some message M on the network is actually an urgent request by simply adding a prefix to this message. Once the adversary receives such a message, he is still free to communicate with the environment in arbitrary ways. However, we have blocked all unintended communication paths to the protocol until the adversary provides the expected response. Afterwards, the protocol run can just continue as expected. So if we go back to the previous slide where I introduced the non-responsiveness problem and showed you several types of possible distinguishing attacks, then we can see that using our framework, none of these attacks work anymore, but the adversary rather behaves as a real adversary. He is no longer more powerful than any real adversary. So our framework provides a very natural solution to the entire problem, and at the same time it's quite simple. It's really just adding a tag to a message to get an immediate response, and it does not involve any additional complications that one has to show during security proofs. It can even be applied retroactively to the literature. So for example, if we have some functionality from the literature which is formally underspecified, we can use this framework to make sure that the specification actually is formally correct. And it is model independent. We have exemplified this by applying it to the three major models of the UC model, the IITM model, and the GNUC model. In case of the IITM model, we also provide full details, including formal definitions of urgent requests, responsive environments, and responsive adversaries. We define various security notions from the literature in this framework and show that all of them are still equivalent, which serves as an important sanity check for our framework. Of course, all security notions are still reflexive and transitive. And perhaps most importantly, we have shown that even though we reduced the power of environments and adversaries, they are still strong enough to show all composition theorems of UC frameworks. So let's go back to the examples from the literature and see what our framework can do for them. Here we have the ideal functionality for non-interactive key exchanges again. And this functionality uses an init request to receive a session key. If we simply add this single tag to the init request, we are now indeed guaranteed that the next message that it receives will be the session key. So from the point of view of a higher level protocol, the adversary is no longer able to interact with any higher level protocols that use fNIC to generate a key. So from the point of view of a higher level protocol, this functionality now is indeed non-interactive. In case of the ideal functionality for signatures of knowledge, if we add this respond tag to the setup requests, we are now guaranteed that we will receive all algorithms immediately. The adversary is no longer able to let this functionality operate with undefined algorithms. In case of the ideal functionality for certificates, by adding this respond tag to the verify request, we make sure that the adversary cannot change state of the signer anymore. So in particular, it also cannot let the functionality accept invalid certificates. Of course, we can also apply our framework to the realization of this ideal functionality. In this case, we change the urgent requests of FSIG, and now FSIG can indeed provide an immediate response to signature requests. The adversary can no longer interact with the protocol in between, and FSIG can now model properties that are present in its realization. So to summarize my talk, protocols very often use urgent requests to exchange some purely modeling related meta information, and because these urgent requests do not exist in reality, so a real adversary cannot abuse them for any attacks, it would be very natural to also require the same from our adversaries in the security model. However, they are in fact more powerful. They can abuse these requests to try and distinguish the real from the ideal protocol. Dealing with this problem leads to complex protocol specifications and security proofs. There is no simple and general solution that can just be plugged into the protocol specifications to deal with this problem. It limits the expressiveness of UC models, and perhaps most importantly, because it's so very unnatural to think about this stuff, it has often been ignored in the literature, leading to underspecified protocols, flawed proofs, and functionalities that are hard to reuse for other real protocols. We provide responsive environments to solve this problem entirely. They are very easy to use. They really just involve the single tag that you can use to prefix messages, and then everything works as expected, and they can even be applied to literature retroactively where problems are. We want to encourage you to use our framework. It just makes your life so much easier by bringing the adversary from our security model to the level of a real adversary. Thank you very much for your attention.
Is there any question? If there is no question, let's thank Daniel again. So we move to the second talk, which is called Shuffle Argument Securing the Generic Model by Prasudi Fauzi, Elger Lipma, and Michal Zayach. And Michal is giving the talk.
Yeah. Hello, everyone. Let me talk about our result, shuffle argument securing in the generic bilinear group model. So what we achieved basically is a new efficient CRS-based non-interactive zero-knowledge shuffle argument. And this argument is over 4 times more efficient in verification than previous work. And here we argue that the verification time is much more important than proof time. It's because usually in the non-interactive zero-knowledge setting, you usually prove once something, and then you probably need to verify many times or by many participants. And our soundness proof holds in a generic bilinear group model. And this is quite complicated. The proof is quite complicated, as maybe there's no high math in here, but the level of complication comes from the huge number of polynomial equations. So we used the computer algebra system to solve it. Especially we needed to go through Grubner basis. So let me talk about motivation for for shuffle arguments. One of the motivation is e-voting. In the e-voting, we have voter, say Bob. Bob wants to vote in some kind of elections, so he uses his computer to send his vote to some server, and then the server counts the votes, and everything is perfect. But as history tells us, it's no voters who counts, but who counts the votes, right? So Mixnet give us two properties, anonymity and correctness. Correctness comes from the fact that data is public, and anonymity comes from the fact that data and source of the data is private. Okay, so simple Mixnet. We have a few voters. Voters send encrypted vote to a mix server. A mix server then gets some random permutation along with randomness R, and what the mix server does is he gets input ciphertext permuted using permutation pi, and randomize them using randomness R. Then the server sends it further to another Mixnet server, say mix server, and the next server does exactly the same, but of course it chooses permutation phi and randomness at his own. Then everything goes to some decrypting machine that knows secret key, and this machine publishes plain text. Of course, we can have much more mixed servers here. The security assumption here is that if at least one server is honest, then the security holds, then the data is private, and then it's correct. Okay, so this setting gives us privacy against each individual server, because if this server is honest, the next server knows nothing about which ciphertext comes from which user, right? But, okay, what if a server cheats? So here we cannot do nothing in this setting. So we need to change it a little. We give every mix server additional public key, and we demand that every server proves that he has done this this shuffling work correctly, so that he honestly output permutation of ciphertext. It means that in fact these D here are re-randomized ciphertext C. Yeah, and send this proof sends proof with new ciphertext to the next mix server. The next mix server verifies all previous proofs, shuffle ciphertext, and sends them on. And in the end, the decrypting machine verify all proofs. Okay? So here we see that the verification time is more important, because every server proves once, but it verifies all the proofs from the servers that were in this line before him. So in this setting, we have both anonymity and correctness. Okay, so shuffle argument, we give efficient zero-knowledge argument of correctness of shuffling. As I said, the mixed server permutes ciphertext, re-encrypts them, and provides a proof that it was done correctly. But the problem is that in the CRS model, existing arguments were not very efficient. Here we have a small comparison. In this paper, we achieved much better CRS length, and it matters because this n here is a number of ciphertexts. So in a national election, for example, it can be like 10 millions, 20 millions, or more. In communication, we do much better, and here, compared to Fauci-Littma paper, we do a little bit worse in terms of prover's time. But on the other hand, we are much better in this in verification phase. Furthermore, we achieve full soundness, and we work in the full generic bilinear group model. Usually, in shuffle is a quite shuffle argument is quite complicated. So usually, known assumptions about bilinear groups are not enough. They don't fit well because they are like they're usually quite simple, and they don't give us the all properties we needed. So up to now, it was usually the case that that the shuffle arguments use some quite new bilinear pairings assumptions, or even introduced a new one. So we get rid of this these assumptions in some sort of way. Okay, so I think this slide appeared a few times already on this conference, but let me remind you what is zero knowledge in a CRS model. So we have a trusted third party that produces CRS, common reference string. We have a prover here and verifier here. So the trusted third party sends the CRS to both parties. Prover knows some instance of problem along with witness, while verifier knows only the instance of a problem. Then prover sends a proof pi that in fact X belongs to some language L. He proves that he knows witness W. Okay? And then verifier accepts or rejects. Of course, as in every zero knowledge setting, we need simulator. In the CRS setting, simulator is given some additional power called trapdoor. And the simulator, who knows trapdoor but doesn't know witness, simulates the proof that X belongs to the language. Okay? So basically, we have three properties of every zero knowledge argument. Is correctness. That means that the verifier accepts if the proof is correct. Soundness. That means that it's hard for a malicious prover to make verifier accept if X doesn't belong to language. And zero knowledge is defined by this simulator. Okay, so let me tell you something about bilinear pairings. Bilinear pairings, so we have three groups of the same order. We denote them by G1, G2, GT. We know generators of these groups. And we have bilinear map. It's a function from G1 product G2 to GT. And the requirements are that they're efficiently compatible, non-generate, and of course bilinear. Okay. some assumptions about pairing is, the very basic assumption is that inverting pairing should be hard. So given pairing on A and B, it's hard to compute either A or B. So this is like equivalent to discrete log. Given G to the A, it's hard to compute A. But what else should be hard? It's not enough. So in a shuffle world, it usually looks like this. We have some protocol. Then we have a bunch of assumptions on bilinear pairings. There are hundreds of them, and many of them introduced in the last few years. But as I said, the shuffle argument is a quite complicated argument. So to make protocol efficient, we usually needed to introduce some bunch of new assumptions. And how to verify these assumptions? No, usually we verify them in a generic model. So it's like a minimal requirement for an assumption to hold in a generic model. Okay, so this setting is not bad if these assumptions are well known and well justified, or if we don't introduce many new assumptions. But in fact, here we need to make our, to bend our protocol to make it fit to these assumptions. So it comes with loss in efficiency. So what we use in this work is a pure generic model. So we were able to simplify this picture to this. Okay. So we know that the generic group model holds only for some restricted adversaries, but on the other hand, it's very, very efficient. Okay, so in a generic bilinear group model, you have this assumption that this adversary has only restricted access to group elements. Like he knows group operation, bilinear map, and can do equality tests. And if he wants to compute some element in G, he needs to know two elements in this group that gives him this element. So basically, if there is an element in a group, in a bilinear group model, then we know the discrete log of the polynomial that creates this element. Well, in general, in a generic bilinear group model, we use GT as a generic group. Here we use in something called generic bilinear group model because we don't handle GT as a generic group, and this comes from the fact that a lot of bilinear pairings has this group GT as some finite field, so it's hard to restrict access to elements of finite field. Okay, so how soundness in GBGM looks like. So trusted third party chooses some number of random variables and produces CRS. CRS is a set of polynomials on these variables, and everything is given in exponent. Okay. Then adversary can get elements from the CRS and make any linear combination of it. And then what we do is we do some quadratic tests. We use bilinear maps, and we check whether our verification equation holds. So we need to make sure that every verification equation is 0. So in general, adversary chooses coefficients HIA, and then we check this set of equations. And we need to show that the solution we get, the only solution we get, is somehow nice, and that means that adversary cannot deviate from the protocol. So when we constructed argument, we need to decompose it to the smaller building blocks. We decompose it to the sub-arguments, and we demand that every sub-argument is efficiently verifiable. So we make sure that every sub-argument is sound independently, and then of course, it may be the case that we need some CRS elements to prove soundness of one argument, and the CRS used in every argument separately is not the same CRS. So we need to compose all the CRSs into one big CRS. But then, if we add element to CRS, adversary becomes more powerful, right? So we need to check again whether this protocol is sound. And if it's not sound, we usually add a new random variable that will be used only in this sub-argument. Okay, so our sub-argument goes as follows. We start with a permutation matrix argument, and in this argument, prover commits to some permutation and proves that he committed to it correctly. Then there comes consistency argument, where prover proves that he used the same permutation as he committed to shuffle ciphertext, and validity argument, where prover gives proof that ciphertext are formed correctly. So correctly means that the soundness proof holds. So in fact, he cannot a little like deviate, but altogether we make sure that that he doesn't. Okay, so let's focus on the permutation matrix argument. So what's permutation matrix? I think it's clear. So we use two sub-arguments in this sub-argument. First, that the matrix is stochastic, so the rows sum to one vector. And then each row is one sparse, at least that at most one coefficient is non-zero. Okay, so one sparsity argument looks as follows. Prover commits to elements in a, it's basically it's a Pedersen commitment, but in exponent in this notation. Then comes argument from the square span programs. Proofs looks as follows. And verification equation is just a quadratic equation that uses these AIs, some elements from CRS, okay? Uses the proof given by a prover, and then checks whether this equation equals 0. But of course, adversary can deviate from the protocol. So here's the form of AI given by a honest prover. But in fact, adversary can produce AI in a very different way, right? So as I said, he can get coefficients next to every element from CRS as he wishes to. So he can produce his own AI in a very sophisticated way. the same comes with A2, and of course he is not restricted to the previous way of getting pi. He can, as previously, get every linear combination of CRS elements he wishes. Okay. But still, the verification equation is out of his hand. The verification equation is like given in a system, and it's checked by a verifier. So it's still the case that this verification equation holds. Okay, and as I said, the idea of the proof is to make sure that here, let's say here, the adversary cannot come up with something different than honest prover. Okay. Okay, so how solving system of polynomial equation looks like. So we need to find coefficients such that this verification equation holds. And we begins with noticing that next to the every such variable built from the product of variables, it is randomly, it's linearly independent. So we can focus on coefficients next to the such tuples. Okay, so we know that if the whole verification equation is to be 0, then every coefficient next to the such tuple needs to be 0 also. This gives us a system of polynomial equations, and the system is huge. I mean, maybe 20 polynomial equations is not huge, but let me remind you that we are talking about sub-argument of sub-argument. So altogether, we have a lot of polynomial equations. So that's why we use computer algebra system. So this is an exemplary system of equations. And here comes the solving. So we mix computer algebra system with manual labor. But that is probably we are not so good in coding. Maybe we can get everything from this CAS system. And we use linear independence of polynomials given in CRS to split some coefficients to make to get more and more equations, but simpler ones. We compute the Grubner basis and then solve the Grubner basis, and this can be, of course, done manually, but we use the computer algebra system. And finally we obtain that this AI is in fact as honest prover would produce. Okay, thank you very much.
We have time for one quick question.
In terms of communication, or? Okay. Okay. So let me begin with the fact that the Bayer graph is a very nice protocol, but is interactive. In terms of communication, well, I'm not sure how we compare to Bayer graph in terms of communication. I'm trying to go back to the table, but communication is well, there is some problems with communication, because in every case of shuffle arguments, you need to send over the web like millions of ciphertexts, right? So basically, the order of magnitude is still pretty bad. There's still a lot of stuff we need to send. So we didn't focus it very much. Well, I think I I skipped it. Okay, so where it is. Well, communication 7 and plus 3. So I don't recall now how this looks like in the Bayer graph settings. Oh, right, because they don't use, right, they have sublinear stuff. Yes, yes, so we do worse, much worse here, right?
Okay, let's thank Michal again. We move to the next talk, which is called Efficient Publicly Distance Bounding Protocol by Handan Kilinc and Serge Vaudnay. And Handan is giving the talk.
Good morning, everyone. Today I'm going to present you our new distance bounding protocol, as you see from the title. First of all, I want to give a quick introduction about distance bounding. So all of the applications that you see on the slide are actually in our daily lives. And the common feature of all of them is that they let us to authenticate without contact. Unfortunately, all these applications are vulnerable for relay attacks. I want to explain it with this following scenario. Here we have Butters, our victim, and also we have our adversary Cartman here, and Butter has the credit card. And Cartman just comes close to our victim, and then yeah, he has also his phone. And we have also Cartman's friends in the supermarket, which waits the signal from Cartman. And after they pair the phone and credit card, and also this phone and the payment terminal, Cartman receives the signal from Butter's credit card, and then just relays it to his friend's phone, and his friend's phone relays it to the payment terminal. And the same happens in the reverse order as well. Like that, in the end, Cartman is able to do payment with Butter's credit card without his permission. So the most promising solution for this is distance bounding protocol. And it was introduced by Brands and Sean. And this has very simple idea. We have two parties, verifier and the prover. And in distance bounding, prover authenticates himself and also proves his proximity. And we have two types of distance bonding, public key distance bonding and symmetric key distance bonding. In symmetric case, the verifier and the prover share a secret, and in the public key case, the prover and the verifier know each other's public key. And in most of the application, it is more feasible to use public key distance bonding because we cannot always assume that the two parties share a secret. However, public key crypto has some problems. It is slower than symmetric key operations, and also the devices that we use distance bonding has limited resources. Therefore, it is very important to construct efficient public key distance bonding. So we want to have less public key operation while preserving the security. And this is the outline of my presentation. First, I will give formal definitions about public key distance bonding. Then I will explain our new weak authenticated key agreement model, which we use in our protocols. And then I will describe our constructions, new protocols, FPKDB and its private variant. And I will finalize my presentation with a conclusion. Okay, first, let's define what is public key distance bonding more formally. So we have a B, it is a distance bound, which is known by all the algorithms in the protocol. And we have two key generation algorithms, KV and KP. They generate secret key public key pair for the verifier and the prover. And also we have other algorithms, verifier algorithm and prover algorithm. In the end of the execution of verifier algorithm, verifier outputs a bit out V, and the privacy output PKP. And out V means that either reject or accept. Now I will describe the security model of distance bonding. We consider several security issues here. The first one is man in the middle. So what's basically we want here that we want to protect honest and far away prover from the adversary. And it is defined with the game. So in the game, we first generate the secret key public key of the prover and the verifier, and sends the public key to the adversary. And in this game, we consider all of the instances of verifier and the provers. What I mean from the instance is that it is each new execution of the prover algorithm and the verifier algorithm. For example, it is an instance where the prover algorithm is run when prover is far away from the verifier, and here is the adversary. And this is another instance where the prover is just close to the verifier, and so on. And between all of these instances, we consider one of them as a distinguished one under the condition that there is no close and honest prover to the verifier. And in the end of the game, if the distinguished verifier accepts the prover and outputs its public key, then adversary wins. And if a distance bonding protocol is man in the middle secure, the success probability of adversary should be negligible. And the other security model is distance fraud. In distance fraud, we want to prevent malicious and faraway prover to authenticate himself. And again, we define it with a game. Here, we first generate the verifier's key and send the public key of the verifier to the adversary. Here, our adversary is the prover. And then prover just generates his secret key and public key with an arbitrary algorithm. Again, we consider all of the instances of verifier and prover. For example, here he is far away, and here he is close, and so on. And between all of them, one of them is the distinguished one, and where we look at the output of this distinguished verifier. And in this distinguished one, there shouldn't be any close prover to the verifier. And in the end, if the verifier, the distinguished verifier, accepts the prover, then the adversary wins. And we want that the success probability of in this game, the success probability of the adversary in this game is negligible. And the last security model is distance hijacking. Actually, this is the more generalized version of the distance fraud. Here, we want to prevent far away and malicious prover to authenticate himself by getting advantage of close and honest prover. And again, we define a game for this model. So we generate the public key and secret key pair of the verifier and the honest prover. Honest prover is represented by P prime here, and then sends the public keys to the adversary here. Adversary is P. Then adversary, the prover, generates his secret key public key pair by an arbitrary algorithm. And as in the previous games, we again considered all the instances. For example, here, honest prover is close to verifier and malicious one is far away. And here, both of them are close, and so on. And between all of them, we consider one of them as a distinguished one under the condition that there is no close and malicious prover to verifier. And in the end, if the distinguished verifier accepts the malicious prover, then this prover wins. And as in the previous games, we want that the success probability of adversary is negligible in this game to have distance hijacking security. Okay, lastly, I want to define the privacy very briefly. So we use HPVP model here. And basically what happens here, we have many provers and adversary. And adversary can corrupt any provers, which means that he can learn their secret key. And in some moment, he just picks two provers and sends them as a challenge. And challenger simulates one of them. And if in the end of the game, if the adversary can recognize who is simulated by the challenger, then he wins. And if a distance bounding is strong private, the adversary, the advantage of adversary in this game should be negligible. And before proceeding the next section, I would like to give the overview of our protocol. So in our protocol, what we do is that the first verifier and the prover agree on a secret S by a key agreement protocol. And then they run a symmetric key distance bounding protocol with the agreed key S. So the part we need public key operation is this key agreement part. And we wonder that what do we really need from this key agreement protocol to achieve MIM security, DF security, and DH security? When we look at the previous key agreement protocol security models, CK and ECK, and also the protocols here which achieves this level of security, we see that efficiency actually is not good. Here efficiency shows that number of exponentiation is done. And we wonder, do we really need that level of security from this key agreement protocol? And the answer is no. Therefore, we defined weak authenticated key agreement. In weak authenticated key agreement, we have only one message, which is sent by the party B. And this message is picked from the distribution D. And after A receiving this N, they both compute secret S by running the algorithms A and B. So this is the framework of one-pass key agreement protocol. And also we define a security model for that by defining a game. And the name of our game is DAKA game, Decisional Authenticated Key Agreement. Here, the challenger first generates the keys for the party A and B. And then also we have Oracle B and Oracle A. So Oracle B is inputted by secret key and public key of the party B, and Oracle A is inputted by secret key and public key of party A. And we have these oracles which runs the algorithm B and A. After the challenger just sends PKA to the oracle B, and oracle B sends n and S0. So n is picked from this distribution, and S0 is the output of B. And also he randomly picks a secret S1. Then he just picks a bit B, and then sends these SB and PKB and PK to the adversary. So here SB is either randomly picked or it is generated by the algorithm B. An adversary can access all these oracles except that he cannot input PKB and N to the oracle A. In the end of the game, if he outputs a bit B prime, and if B prime equals B, he wins. So if a one-pass key agreement protocol is DAK secure, the advantage of adversary should be negligible in this game. And also we define DAK privacy for one-pass key agreement protocol. Here we want to protect the privacy of the party B. So here challenger generates the keys for A and B. And we have only oracle A. After the challenger sends PKA and also secret key and public key of party B to the adversary. Adversary also generates secret key and public key pair for the party B and sends them to the challenger. After that, challenger picks a bit B and computes the message N from the distribution D and runs the algorithm B either from the secret key that he generated or the secret key public key pair that adversary generated. And then sends the S, the output of B, to the adversary. Adversary can access the oracle A, and in the end he outputs a bit B prime. If B prime equals B, then he wins. If a key agreement protocol is DAK private, the advantage of the adversary in this game should be negligible. So basically, here adversary knows the secret keys, but he shouldn't able to distinguish which secret key is used. Okay. And also we propose a one-pass key agreement protocol, which is DAK secure and DAK private. We call it as nonce-DH. In nonce-DH, we have public parameter, a group, a prime order group, and its generator G. And the parties picks their secret key from ZQ, and the public key is just G to the secret key. After that, the party B picks a message from L-bit strings and sends it to the party A, and then they compute this function H. So if you look at the input of the function H, you will see that they are equal. And we prove that this protocol, nonce-DH, is DAK secure and DAK private in the random oracle model, assuming that gap differential problem is hard. And so now we can look at the previous protocols and our protocol. As you see, we are much more efficient. We only need one exponentiation. We have weaker security, but it's not a problem. It is enough for our purposes because our main purpose to construct a secure distance bounding protocol. Okay. Now I can explain what is our protocol. The first one is FPKDB. Here, prover just picks N from the distribution D and sends N and his public key to the verifier, and then verifier and the prover generate secret S using the algorithm A and B. After that, they run a symmetric distance bounding protocol S using this S that they generated, and after verifier just outputs his message, which means it's either reject or accept. And we prove that FPKDB is the MIM secure, DF secure, and DH secure under the conditions that you see here, the bold ones. For example, when we look at MIM security, we need from SIMDB to multi-verifier one-time MIM secure, and we want from the key agreement protocol to be DAK secure. So what I mean from one-time MIM secure is that it is enough to have security, MIM security even, how can I explain? So if we run the SimDB one time, it is secure. So if we run second time, it is not secure anymore, which is weaker security notion than normal MIME security. So basically what we need from weaker distance bounding protocol SimDB, we can construct a fully secure MIME CDB. And this is the private variant, which is very simple. Here the prover's public key has two parts, PKV1 and PKV2. So here, as usual, prover generates n and encrypts this n with his public key, with the public key of the verifier, and sends it to the verifier. And then verifier decrypts and learns the messages. Then they generate the secret S and run symmetric key distance bounding protocol with this S. Here, PKP is the private output of verifier. And we proved that this private variant of FPKDB is strong private in HBUP model if the key agreement protocol is DAK private and the crypto system is in CCH secure. So I gave you a framework about our protocol. What I said that we first need to use a key agreement protocol and then run a symmetric key distance bounding. So this is an instance of our framework for FPKDB. So for a key agreement protocol, we can use non-CH. The pink part is non-CH. I explained already. And then for a symmetric key distance bounding, we can use OTDB, which is one-time secure distance bounding protocol. And how it works, here first the verifier picks a nonce and sends it to the prover. After that, they XOR the secret S and nonce and get A. And then challenge phase begins. In challenge phase, the verifier sends a bit CI, it is challenge, and starts the timer. After receiving it, the prover computes the response, as like that, and sends the response to the verifier, and the verifier stops the timer. After n rounds like that, the verifier checks if all the responses arrived on time, like that, by checking if the round trip time is less than 2B or not, and checks if all the responses are correct. So if everything is okay, in the end, the verifier accepts the prover and output his message. And I want to conclude my presentation by comparing our distance bounding protocol with the previous ones. So here you see column for security, privacy, and the public key operations needed to compute this distance bounding protocol as number of computations required. So for example, when we look at HPO, and our private variant of FPKDB, we have stronger security and stronger privacy, and we need less operation on the prover side. And the pre-DV security is the same with our private variant of FPKDB, and we are slightly more efficient than this. And also we have one more advantage against PrivDB, which is that we have also non-private variant, FPKDB. Like that, since not all applications requires privacy, in this case it is feasible to use FPKDB instead of private variant of FPKDB. And this is the end of my presentation, and I would like to conclude my presentation with an announcement. So our lab is searching for postdocs. We are at EPFL. So if you want to apply for it, or if you know someone who wants to apply, this is the contact mail. Thank you for attention.
We have time for one question. Just have one. Did you consider to remove the gap assumption using the 2N-Diffie-Hellman tweak?
Sorry, I don't hear.
Did you consider to remove the gap assumption from your protocol using the computational Diffie-Hellman assumption, for example?
we couldn't prove it with computation dependent bits, right? It didn't work.
Even with the cache kills shoop technique?
We didn't try that one.
Okay, let's thank Andan again. So we move to the last talk of the session, which is called Indistinguishable Proofs of Work or Knowledge by Fonteni Baldimci, Agelos Keyas, Thomas Zacharias, and Bin-Chen Zhang. And the talk is given by Thomas Zacharias.
Hello. I will begin my talk with some motivation. So let me get this hand out of my owl. Okay. So the first time that we ran to discuss about this concept was by a simple observation in standard proofs of knowledge protocol. So just to remind you, a proof of knowledge is an interactive proof where a prover convinces the verifier of the validity of some statement. And this is done in a way such that honest proofs always verify. This is the completeness property. And if a prover manages to convince us with some probability, then we actually have a mechanism to extract the witness. And in most interesting constructions, this is done in a prover privacy manner. You can hide the code of the prover, either via zero knowledge or some relaxation like witness distinguishability or some other variant. A very standard and prominent example is the Schnorr identification scheme, which is essentially a proof of knowledge of a discrete logarithm. It runs in 3 moves called the commitment A, the challenge C, and the response R. And it is what we call a sigma protocol, which means it's an interactive proof, public coin, 3 moves, achieves special soundness. It's a strong proof of knowledge property, and soundness proof of knowledge property, and zero knowledge against honest verifier. So what we were thinking is that, okay, we are convinced that actually the prover knows the witness, but how did the prover manage to do that? So what was the way? Did it actually happen to do this efficiently because it had some a priori knowledge, the witness? Or did it actually spend some super polynomial effort to solve this specific challenge? Okay, so we're starting to see it more generally because this is a very special case. Actually, the knowledge challenge and the work challenge are exactly the same, but assume that you want to be convinced that a prover either can solve a problem or it knows something. And where could this be useful? And we ran into the seminal paper from Dworkanauer for proof of work. It was called as pricing functions then. And it was a proposition of how you could have a reducing spam mechanism via these tools. So we have a mail receiver Bob, a mail sender Alice, and a mail server. And we want to have a reduced spam in this mechanism. So what we do is that if Alice is an actual valid contact, then it proves some knowledge that it is runs a proof of knowledge in order to run a proof that it's a contact. And if someone is not, like Eve, for example, then the system somehow forces the non-contact to run for some time or spend some computational results so to be approved. So in this sense, someone who is actually a spam and is not a contact will be discouraged from such an attempt. The problem with this is that there is some leakage in privacy here, because for this to happen with a DN92 approach, the mail server gets to know Bob's contacts. And a very nice idea of how we could advance this technique is how you can do that so that the privacy of the contacts is preserved, so that this is not leaked. So you would use a tool that the senders can prove that either they know something that relates them to the receiver, or they have spent some amount of resources. And this is done in a way that is privacy preserving, which means that the prover's mode, what the prover chose in order to follow and prove, remains unknown. And now I will just tell you that what we define and model as proof of work is via the concept of cryptographic puzzles, where in this sense a verifier challenges the prover with a puzzle, the prover returns a solution, and if the verifier accepts, then this means that he is somehow certain that the prover has spent an amount of work, given that we believe that this problem is somehow hard. And all that somehow came to mind and brought us to this concept that we will call as proofs of work or knowledge, now for brevity POWORKs, where you prove that either you know a witness to a statement or you perform some work, and you do it in an indistinguishable manner. So in more detail, our contributions are, first, we define formally what is a cryptographic puzzle system, and then use this notion to define POWORKs that are now defined with respect to some language in NP and a fixed puzzle system. We will provide an efficient three-move POWORK construction and instantiate our puzzle systems with two different ways. One we use a random oracle way, and one we rely on complexity assumptions. And finally, in order to provide some intuition why this specific new class is somehow useful, we have two real-world applications. First, how you actually said before, reduce spam in a privacy-preserving manner, and how you could build like a hybrid cryptocurrency system with enhanced liveness. And we also provide a theoretical application where you get a 3-round concurrent and simulatable argument of knowledge, which is a definition from process work. So to begin with, cryptographic puzzles. So what we see as a cryptographic puzzle in an informal way is that it's something that you can sample the puzzles and generate them in a fast way, and you can verify them in a fast way, but must be hard to solve. Maybe not intractable, but certainly will have some parameterized hardness. And we will also ask that the puzzles are what we say amortization resistant. This means that if you take a batch of puzzles, it doesn't provide you with some significant advantage with respect to trying to solve them one by one. And for our constructions, we require a special property that we actually prove in our instantiations, that the puzzles to be dense. What we mean by dense is that if you somehow sample randomly from the length of the puzzle space encoding, then it is with high probability you're going to run into a puzzle. And when we mean by proof of work, we don't actually restrict parallelizability, because we're not talking about a specific time here. We're talking about what we generally can be seen as computational resources. So now a puzzle system in a more formal approach starts with 3 standard algorithms, which is a sampler, takes a hardness parameter H, and that puts a puzzle. And there is a solver algorithm that takes the parameter of the puzzle and will output a solution. And there is a verifier that will actually have the parameter, take a pair of puzzle and solution, and will check if this solution is valid. A dense puzzle, also we require to have an extra algorithm that we call sample solutions, which means it doesn't actually only put a puzzle, but a pair of puzzles and solution. Our properties are, first, the easy stuff is that the completeness of the sampler and the correctness of the sample sol should actually happen with the programming probability. It should be efficiently sampleable. What I want to stick a bit more is what we define by hardness. So we define hardness with respect to some scaling function, which means that if I give provide the adversary with a puzzle, then, and he returns with a solution, the probability that he managed to do that in a time scaled by g with respect to the solver that we have is negligible. And let me tell you what I mean. Assume, for example, that our solver is an algorithm that runs some brute force search in 2 to the lambda steps, lambda the security parameter. So the best thing that we could hope for is that G is actually the linear function. So we don't have any scaling with respect to that, but this is not something I would expect. What we would expect is that someone who runs a brute force search, if it does square to the 2 lambda steps, the probability that he actually finds a solution will be negligible. So here, G would be the square root function. Generally, G is sublinear. And for the density and the privacy that we will require in our proofs, we want that the sampling distribution of the 2 sampling algorithms is indistinguishable, and we define amortization resistance with respect to a parameter k, which is the number of the puzzles that you give us a batch, and a scaling function, which of course depends on how many puzzles you provide. So this actually tells us this definition in an informal way that if I provide k puzzle, you don't have an advantage more than a scale of t with respect to solving them 1 by 1. For example, it could be that 1 puzzle takes 2 to the lambda steps, and k puzzles take no more than 1 over kappa to the lambda steps. So if k is polynomial, again, you're still hard. Giving a formal definition of puzzles will actually enable us to show formally what is a POW-work. So a POW-work is an interactive proof, a prover and a verifier, and it is F-sound if it satisfies the following properties. First, the completeness property, which means that an interaction either with the prover running on the knowledge mode, it has the witness, or by having the code of the solver, then this could be accepted with overwhelming probability for valid statements. And actually, I'm sorry for this RL that pops up there. It's not right or left. It's actually witness relation. I have some compiling errors. Whenever I do save and export, it always gets me that. So always something new. I mean, it's like the suitcase problem. You have to put many things in a suitcase, and you squeeze, and something new pops out every time. So this is what happened. And then I said, OK, I cannot deal anymore with that. So when you see right and left, it's the witness relation for L. OK. So, and now soundness is defined with respect to, again, a scaling function f, which means that over the coins of the sampling algorithm, if a prover manages to persuade us within a time which is scaled by f with respect to the time of the solver, then it actually did that because it knows something. It didn't work, it knows. So we can extract it via an extractor. This is f-soundness. And indistinguishability says us that the view of the verifier, it is indistinguishable even whatever the mode of the prover is. Is it the knowledge or the work mode? And this property directly implies the standard witness distinguishability, because every interaction with some witness is indistinguishable with a reference point, which is the work mode. OK, so now with the construction, first to give some intuition of why this notion makes sense. So you can have a trivial 4-round construction by having the verifier sending a puzzle, and the prover with either commit and provide a zero knowledge of the witness, or it can commit to a solution and provide a zero knowledge proof that send a solution. So this can be done in 4 rounds. It is much more interesting to do it in 3 rounds. So we actually have a compiler which takes a 3-round special sound HVZK protocol and a fixed puzzle system, and thus produce a 3-round POW-work. Just to remind you what a 3-move special sound HVZK is, so it is a protocol with respect to some unpaid language. The prover runs again in a commitment A, challenge C, and response R rounds, and will prove the validity of the statement with the completeness property, the special soundness property, which means proof of knowledge in the sense that I have an extractor that if I provide the extractor with 2 accepting transcripts, then we can extract a witness, and we have the zero knowledge against an honest verifier. So how would this construction work? Have in mind that because we want indistinguishability, the 2 modes should appear similar. So see the flow here. What is done is that the prover starts with running the first move of the underlying HVZK protocol. It produces a commitment A prime. It sends it to the verifier. The verifier will send a challenge And now what will happen is and now that's where density comes up. So the prover will sample a puzzle and solution and will set as the challenge of the underlying protocol as the XOR of the verifier's challenge and the sample puzzle, and will run the third move of the underlying protocol given this C prime. And it will output, so the third move of the POW work is the C prime, the R prime, and the pair of puzzle and solution. The verifier will run the following checks. First, that its challenge is actually an XOR of C prime and puzz, and the transcript of the underlying protocol verifies, and of course that solution is accepting. Now we have to go to a proof of work mode that looks the same for indiscussability reasons. So in this case, we use the simulator that is given by the HVZK property of the underlying protocol. It simulates a valid transcript and sends A prime to the verifier. The verifier will again respond with C, but what is going to change now is that now the prover does not the witness, it has to work. And how it will work? It will work by computing a puzzle that it is the XOR of the given challenge and the simulated one. And now, because this is uniform and density happens, this must be a puzzle. Okay, that's why we need dense. So given this puzzle, it will run the solving algorithm, it will output a solution, will send it to the verifier, and the verifier will actually run the same checks. And what is the security that we get here? So given some reasonable assumptions that it's very easy to get, if we require that challenge and puzzle sampling distributions are very close, this can happen for every distribution which is close to uniform, and that solve is actually the slowest algorithm of the ones involved. So what we get is that for this language and of the underlying protocol and the puzzle system that we fix, then if the puzzle is G-hard, we get a POW work which has constant with respect to G-soundness and statistical indiscussability. So what remains now is that, okay, we have our 3-round special soundness VCK protocols, and in order to plug something to our compiler, we need to have the dense puzzles. So let's build some of them. We provide two constructions. One is based on random oracles, and one is based on complexity assumptions. So the first one is actually the first that would come to mind. So what can I think of a puzzle? Let's just think that I have a hash function, and I will require that this, I will give actually as puzzle the last, I have a hardness parameter h, I will give as puzzle, okay, give me the last h bits of, so LSB h means the last h bits of a randomly picked x. So I will give you this as a puzzle, the solution here is x, and now you are going to start running the hash until you find something valid, and of course the verifier will check whether the solution is actually, if you have the solution, take the h bits, it's actually the challenged puzzle. So it's something which is the first thing that maybe will come to mind. And what it buys us is that for some meaningful parameters, like h, the hardness parameter lies between the square root of the square log of the security parameter and L/4, and for some constant c which is greater than 2, and some quite big k, we get that in the random oracle model, this has a c root soundness. That's the scaling we get for every c greater than 2, and it's actually amortization resistance with respect to the identity function. That's what is ID, so we don't actually have any loss there, whenever the batch of puzzle is no more than k. A more interesting construction is how to go to the complexity assumption setting. So here, we are going to build our construction based on the hardness of one-way related primitives and discrete log. So we construct, so we start with a universal one-way hash function. This is a universal one-way hash function. Is a one-way hash function with a specific property that you can actually, an adversary cannot actually plug into two inputs that have the same evaluation. So this is target collision resistance, and we build an extractor that has a similar property. And this can be seen as independent interest, And now, given that we have these TCR strong extractor and some arbitrary one-way function, we get that this function, we don't have to get into details, but this function is actually a dense one-way function. What we mean by dense is that it is output, it's close to uniform. Not only it's one way, but it's somehow very beautifully distributed in the range. And now that we have all the tools, what we do is we somehow instantiate this f with a well-known one-way function, so we get the inverse of the log, and our puzzle is actually this one-way function and some parameters that, some randomness which is used for refreshing the puzzle, and the solution is required to have the length of the hardest parameter. So again, what we have is that, I'm not going to go into so much details here. So the parameters regarding security of these constructions are similar with the previous one, but now we assume some reasonable hardness assumptions for the extractor and the discrete logarithm. And just to tell you that for these specific parameters, this hardness of the log holds in the generic group model. You can take another assumption if you like, but we just provide this and an instantiation because this is actually what Soup's results tell us. And I will continue with some applications, which is actually the last part of our contribution, to show why this complexity class makes sense. So our first application, coming back to the intro, is now that we can use directly a POG work, not completely directly, but quite easily, and have what we liked in the first place, that we have a reducing spam mechanism that the prover does not actually reveal its mode of proving, so it is a privacy-preserving reducing spam. Another interesting maybe application is how we could build a cryptocurrency that has robustness, has enhanced liveness property. And how could this happen is that most blockchains use a decentralized public ledger that runs proofs of work, okay? There has been some counter-arguments against this overwhelming use of resources that is expanding. So there are some new constructions that are based in signatures, which can be seen as proof of knowledge of some secret key that you hold some income. So what if we could build a hybrid case? What do we mean by a hybrid case? Assuming that you have a system that runs normally via standard proof of work method, but something happens and most of the miners go offline. We would like somehow to the ledger to remain live here, to present this liveness property of the blockchain. So we could have something like a trapdoor, like a backup, which could be a party, a trusted party that could use the proof of knowledge mode and issue blocks in case of such an emergency, and then again go out if this emergency doesn't hold anymore and revert back to the proof of work setting. This doesn't mean that this is not essentially a decentralized proof of work approach. It means that it is like a proof of work with a backup in order to enhance liveness. We can discuss whether if this is interesting, but you can do that with a POG work, and you can do that in a way that you can hide whether this emergency happened. And so you can hide every possible impact that could happen to the economy if someone knew that blocks are being issued because the miners are down. So this is not revealed. And our final application, we use pass as a result, and to show that, pass result have some very interesting notions of simulatability, like a somehow meaningful relaxation of zero knowledge. And we show that under reasonable assumptions about what could be the hardness of our puzzle, actually every hard puzzle should satisfy them, then our POG construction is a straight line simulatable protocol. And since this is a closed standard polynomial class, this lambda to the polygon log L time, then we plug in the results of pass, and we get a 3-round concurrently simulatable argument of knowledge, which actually reduces by 1 the 4-round construction for the same primitives that original pass had in their paper. And some conclusions on future work. So as we said, we defined POG works. We did it via defining puzzle systems and had instantiation and constructions, and we provide some applications. And some interesting future directions that we can think of is why not having some alternative POG work constructions why not seeing the relations of this new notion with the other known complexity classes, some more applications in the real world would that actually give more boost of why it's nice to use such a primitive, and new puzzle system associations that could plug in so that we have a flexibility of which is the setup setting that we could plug in our hardness arguments. And that will be the end of my talk. Thank you very much.
Is there any question?
You're to run searchable encryption, you mean?
Yeah, something like that.
And what would be the proof of work method? So the reduced mechanism?
Well, I suppose it wouldn't have to be in that respect. So you could still run the proof of work inside, but you wouldn't have to worry about the proof of knowledge because you've got that.
I don't have actually a direct answer. I'm not saying that it cannot be done by that. I cannot have set up the efficiency here. I'm not saying that it cannot be in another way. Maybe you can plug in searchable encryption and work, but this is somehow more straightforward. Like it was like the natural extension. So you can use proof of work with and prevent spam. So it's a way to do it. Okay, it sounded meaningful, and in the seminal paper of proof of work, this was the main motivation. Use this to prevent people that are not actually likely to be your family, whatever that means, so that you prevent them from doing stuff. And now let's do that. Why? Let's extend this nice motivation that actually was the initiative for doing all this proof of work modeling stuff in the paper. So let's try to do that in privacy-preserving manner. Whether it is faster to do it with searchable encryption in a symmetric setting, I don't know if it makes sense, because I know that searchable symmetric encryption is fast, but I don't know in a public setting if it would be more efficient than what we do now. But again, I don't have a direct answer. I have to check about this.
Okay, let's thank Thomas again and all the speakers of the session.
Thank you. And I also have to give the most expensive stuff.
test. つけて。あ、確かに。うん、そうですね。これをありがとうございます。カメラが。テスト。Hello everyone。
聞こえないな。ちょっと遠いかな。自分で持ってもいいけど。
じゃあ持って話します。これで。このマイクを使われますか？何でもいいんですけど。じゃあ終わった後、はい。わかりました。
Okay, so welcome to the last session about multi-party computation. The first talk will be about size hiding computation for multiple parties by Kazumasa Shinagawa, Koji Nuida, Takashi Nishide, Goshiro Hanoka, and Eiji Okamoto. And Kazumasa will give a talk.
Thank you for the introduction. My name is Kazumasa Shinagawa from University of Tsukuba and AIST. I'd like to talk about size hiding computation for multiple parties. This is a joint work with Koji Nuida, Takashi Nishide, Goichiro Hanaoka, and Eiji Okamoto. In secure multiparty computation, each party, Pi, has some private input, xi, and the parties wish to compute a function y equal f of x1 to xn without revealing the inputs. In this talk, we will consider the case, the single output, that is, all parties wish to compute the same function, and assume semi-honest adversaries, and the number of corruption is up to n-1. The size hiding computation, which is the main target of this talk, is a secure multiparty computation protocol that can hide some of input and or the output sizes from some of parties. Each private size can be hidden from different set of parties. So there are many types of size hiding, but it is well known that some of size hiding is impossible in general. So it arises a natural question, which type of size hiding is possible in general? In this talk, we give a complete characterization for the feasibility of size hiding multiparty computation, assuming the existing of FHE. Specifically, we assume the FHE with circuit privacy. Before proceeding the technical details, I will show the two applications for size hiding computations. The first one is the set intersection protocol. Suppose that the police has a list of terrorists, X, and the company has a list of customers, Y, and the police wants to compute the intersection X and Y without revealing the size of X. And the size of X is related to the number of terrorists. The naive approach is padding approach and use the standard multiparty computation protocol, but it is inefficient because the complexity of the protocol depends on the upper bound of the input, even when the actual input is very small. The other application is a millionaire problem. Suppose several aliens wish to compute which planet has the largest population, and the population is related to the military power in the planet. So they wish to hide the population. Moreover, the input size is also related to the military power, so they wish to hide also the input size. In this case, the padding technique doesn't work because the largest population in the universe is too large. Okay, this is the outline of this talk. I'll first introduce notations for size hiding, and I'll explain the previous result for two-party setting. And I will give the complete classification for multi-party computation protocol, but in the standard model, almost all sizes cannot be hidden. So to circumvent this impossibility result, we introduce a strong secure channel model, which is a new model. And it is implementable by steganography. And finally, this is our main contribution. We give a complete classification for multi-party computation protocols in the strong secure channel model. The fact, our theorem shows that many sizes can be hidden in the strong secure channel model. Firstly, let me introduce notations for size hiding. If there is an edge from the party I to the party J, then party J can know the size of xi. Conversely, if there is no edge from party I to J, Pj must not know the size of xi. And we also consider the case some parties must not know the output size. We denote such a party by the cross circle. This is an example of a size hiding class. Hereafter, we call such a graph a size hiding class. In this class, party 2 must not know the size of x1 because there is no edge from party 1 to 2. And party 3 must not know the output size. So this class has two private sizes, the private size x1 and the output size. And we say that a size hiding class is feasible if general multiparty computation is possible in the class. And we say that a class is infeasible if it is not feasible. Okay, I'll explain the previous result given by Lindell, Nissim, and Orlandi, ASIACRYPT 2013. They showed that hiding two or more sizes is infeasible in two-party setting. Specifically, they show that the left classes, these classes have at most one private size are feasible. And the right classes, they have at least two private sides are infeasible. Okay, this let me explain our first result, the classification for multiparty computation. This is the extension of the LNO13. And we showed that even in the multiparty computation setting, it is infeasible to hide two or more sizes. The infeasibility is proven by techniques of LNO13. And the protocol, the feasibility, the protocol for hiding the one input size is the following. The first, all parties invoke key generation protocol for threshold FHE, and each party, PI, sends encryption of XI, that is ciphertext of threshold FHE, to the party 1, who has the private input size. And party 1 then computes encryption of Y. Y is the output value using homomorphic evaluation algorithm, and broadcasts it. Finally, the parties invoke decryption algorithm, and they can obtain the output value. This is a protocol. Okay, but in the standard model, it is impossible to hide two or more sizes. It is very strong limitations. So next, I will explain the intuition why multiparties do not help size hiding. This is a size hiding class which is proven by infeasible. If we add the additional party P3 who can know both the size of X1 and the size of X2, but this class is still infeasible. Why? Party 3 can know the size of X1 and the X2. However, P1 cannot send encryption of X1 or message of length related to the size of X1 because the channel between the party 1 and 3 may leak the message length to the party 2. This is a limitation of the standard channels. To overcome such a limitation, we introduce a new model, the strong secure channel model. In the standard secure channel model, the adversary cannot obtain the entire message, but he can know the size of message. In the strong secure channel model, adversary cannot know even the size of message. Such a channel can be implementable by steganography, so it is considered to be reasonable model. Okay. Next, I will explain our main result. That is a complete classification for multiparty computations in the strong secure channel model. In the strong secure channel model, any sizes, any the number of parties, any sizes can be hidden in the maximum sense. For example, this size hiding class has 3 private inputs. Remember that if there is no edge from this party to this party cannot know the input size of this party. So in this class, all of input sizes are private. So this class has 3 private sizes. However, it is infeasible in the secure channel, but it is feasible in the strong secure channel model. Several types of some of classes are still infeasible, even in the strong secure channel model. This size hiding class is one of the such class. I'd divided our theorem into 2 cases when the output size is public and the output size is private. So I will explain the first case when the output size is public. In this case, size hiding computation is feasible in the strong secure channel model if and only if for every parties I and j, there is an edge from I to j or j to I, or there is a party k that satisfies there is an edge from I to k or j to k, I to k and j to k. This triangle case is feasible because every pairs are connected. So this graph satisfies these conditions. On the other hand, this such a size hiding class is infeasible since this party and this party, diagonal parties, does not satisfy this condition. Let me explain the main idea for construction in the case of 3-party triangle setting. The key idea is sharing protocol. Just the sharing protocol for party 1 is the following. First, party 3 sends to party 1 the ciphertext of x3. This bracket means a ciphertext of threshold FHE. P3 computes the concatenation of flag and x3, and P3 sends to P1. This is okay because remember that there is a party 3, there is an edge from party 3 to party 1. So the party 1 can know the size of x3. So this step is okay. And party 2 sends to party 1 the following ciphertext. If the size of x1 is greater than or equal x2, then the party 2 compute the ciphertext of x2 with padding and with flag. If the size of x2 is greater than the x1, then he computes the 0 ciphertext. The party 2 can know the size of x1, so P2 can do this. And this is okay because the both ciphertext, the length of both ciphertext is related to the size of x1 only. and invoking sharing protocols for P1, P2, and P3, one of them can obtain all flagged ciphertext. Specifically, the party who has the largest input can obtain all flagged ciphertext, and the party can compute the encryption of the output. This is the main idea for construction. I will explain the infeasibility in the case of square size hiding class. Suppose this class is feasible, and let capital F equal small f of x1, x2, and let PA, party A, is the joint party, the party 1 and party 3, and party B equal party 2 and party 4, then this protocol for capital F is two-party protocol for small f, and this class has two private sizes because the in this case x3 and x4 are dummy inputs, so party A and party B cannot know the input size of the other party. However, it contradicts LNO 13, so this size hiding class is infeasible. I will explain the case 2 when the output size is private. In this case, size hiding computation is feasible in the strong secure channel model if and only if for every party who must not know the output size, the party can know all input sizes, and there is a party who can know the output size. The party satisfies this condition. This is a feasible class because these parties can obtain all input sizes, and this party can know the output. This party can know the input size of this party, and this party can know the input size of this party. So this graph satisfies this condition. This is an example of infeasible class. All of parties must not know the input size of this party. So the latter condition does not satisfy in this class. Okay, I will explain the main idea for construction in the case of this size hiding class. The key idea is to combine the security of FHE and the MPC. We take two strategies. The P3 and P4 are not involved in key generation algorithm because they must not know the output size, so they must not join threshold decryption algorithm for the ciphertext of Y. And they do evaluation protocol using MPC and obtain the ciphertext of Y with 0 paddings. Thanks to the padding, they can do this without knowing the output size. This is a flow of the protocol. Firstly, P1 and P2 invoke key generation algorithm, and P3 and P4 get encrypted input shares. And using these shares, they evaluate using MPC. And finally, and P1 and P2 invoke threshold decryption for the ciphertext that can generated by this step. The key observation is the following. And we note that in this case, in this talk, we assume adversaries can corrupt up to n-1 parties. So in this case, 3 parties. If P1 and P2 are corrupted, then FHE does not work. But in this case, the security of the protocol is derived from the security of MPC. And if these parties are corrupted, MPC does not work. However, the security of the protocol is derived from the security of FHE. So FHE or MPC guarantees the security. So it works correctly. And let me skip this slide because this step is similar to the case 1. Thank you for your attention. That's all.
So any questions or comments? Okay.
I was wondering if you considered adversary structures that can help achieve size hiding computation.
Oh, sorry. Could you repeat again?
Yes, I was wondering if you've considered adversary structures, so not necessarily corrupting n-1, but corrupting subsets, and if that can help you achieve size hiding computation if you assume that certain sets of players can be corrupted and not others. So, for example, you can corrupt the first and the second player, or you can corrupt the third and the fourth player, but not. So if those types of things can help with size hiding computation.
I don't understand your question. So please talk about in the offline.
Okay, any question? Yeah.
I hear you use steganography. Please tell me how data hiding scheme to use to implement your model.
Could you speak? Could you repeat again?
How to use data hiding?
How to reduce data hiding?
Yes. How to use data hiding to implement your model?
Sorry, the last part is what is the last part?
How to use?
How did you?
Which data hiding scheme you use to implement your model?
Which?
Type of data hiding scheme.
Anybody translate Japanese? The strong secure channel model is considered to be implementable using steganographic techniques, but the concrete construction does not exist. So it is one of the open problem to construct such a strong secure channel model. Does it make sense?
Okay, we ran out of time, so thanks
Okay.
to customers again.
Thanks.
Okay, the next talk will be about how to circumvent the two ciphertext RoboBow for linear garbling schemes by Kamen Kemkar, Leo Kikuchi, and Kotaro Suzuki.
Yes. I will use
And
this one.
Leo will give a talk.
Okay. Can you hear me? Okay. Okay, so today I will talk about the paper entitled "How to Circumvent Two-Ciphertext Lower Bound for Linear Garbling Schemes." This is a joint work with Kamen Kemfuka and Kotaro Suzuki. All belongs to NTT Corporation. Here's the agenda of this talk. So first, I introduce a lower bound and briefly explain our result. Let's get started by introducing the garbling scheme. The garbling scheme is a mechanism to evaluate a circuit without knowing truth values. For example, we consider garbling single AND gate. Single AND gate. The left side is represent a plain AND gate, and the right side is a garbled AND gate. If each truth values is encoded to the k-bit random values, KA0 and KA1, and this is a random value, so one cannot inverse the truth values. And in this example, garbled gate contains 4 ciphertexts. Each ciphertext contains one of output keys, and one can decrypt one of ciphertext in evaluating the circuit, in the evaluating garbled circuit. For example, the input is 0 and 1, the output is 0, and in the garbled circuit, input is KA0 and KB1, and one can decrypt the second ciphertext to obtain KC0. In the classical scheme proposed by Yao, contains 4 ciphertexts per gate, and each element is k-bit. So this contains 4 k-bit per gate. There have been several studies to reduce the ciphertext size. For example, GR3, GR2, free XOR, and recently the Hall, Roslek, Evans proposed a half-gate scheme that is the most efficient. This costs 2k bit per AND gate and 0 bit per XOR gate. And in addition to the proposed half-gate scheme, the Hall et al. Also proposed a lower bound of the size of garbled circuit. They first define the linear garbling scheme that captures all practically efficient garbling schemes. And they say they prove the lower bound that says a linear garbling scheme must have 2 k-bit ciphertext per AND gate. And of course, as shown in the previous slide, half gate achieves the bound. So half gates seem to be optimal from the lower bound. However, in this paper, we propose a linear garbling scheme that requires strictly less than 2 kbit ciphertext per AND gate. You may think that this result is a contradiction of the lower bound, but we think that this scheme does not contradict, but rather circumvents the lower bound, because the proof of the lower bound assumes, implicitly assumes that each element, each ciphertext is a kbit. But our scheme requires only 1 kbit element, but actually do require 4 2-bit ciphertexts. So the total is 5 ciphertexts. So we think that our result is not break, but circumvents the lower bound. Okay, next, we want to explain how to garble single AND gate. Before I explain precisely, I'd like to introduce one basic observation. In a garbling scheme, we often use a kbit element as a key and ciphertext and so on. And kbit element can be regarded as an element in not only GF22K, but also the subscript 22K. It means that we can use 2 operations on kbit elements. The one is an operation in div22K is a bitwise exclusive OR. It means that, for example, 0011 O plus 0011 equals or 0. And the other is integer addition. For example, 0011 O plus 0011 equals 0110, which is different from the other. Okay, we explained the setting of the garbling on single AND gate. We will try to garble single AND gate with with single kbit ciphertext G. And for the efficiency reason, we want to all operations consist of hash function, addition, plus, and O plus. Okay, so next I explain how to garble AND gate is. We give an illustration on evaluating and garbled AND gate. The first, there are 4 cases in the input 00 keys and 01 and 10 and 11. And these keys are evaluated with ciphertext G, and finally one obtains the output key. For now, we consider AND gated, so the 3 of 4 input cases should be mapped to the 1 values, and the last case, when the input is 1, 1, should be mapped to the KC1. So the first is we want to define the input-output keys and the evaluation function satisfying this map. So the first one is using free XOR-like definitions. We first define the 1 key is 0 key O plus delta, and the evaluation is a hash function. If we define so, the second case and the third case are mapped to the same values, because K0 plus KB1 equals K0 O plus KB1 equals K1 plus O plus KB0. And in addition, to map the first cases to the same value, we set the ciphertext C as this. If so, this hash value is cancelled and mapped to the same values. Okay, at this point, the mapping is constructed. But however, you know, this scheme is clearly insecure, because from the KA0 and KB0, both output keys can be generated because, of course, KA0 and KB0 can be evaluated to the KC0, and KC1 value is equal to the hash of KA0 plus KB0 because this equation holds. To avoid this problem, we use plus instead of O plus in hash. We redefine the one key as a 0 key plus D. If so, inside of hash function we use plus. If so, the one key is to be the hash of KA0 plus KB0 plus 2D. That cannot be derived from the KA0 and KB0. This construction avoids the previous problem, but that is still be insecure because ciphertext G is only used in the first case. So if the ciphertext G is used, an adversary may know that the input is 0, 0. So the next idea is I use ciphertext G in evaluation with probability half. We additionally introduce a choice bit, B0 and B1, and the output key depends on this choice bit, B0 and B1. If so, all evaluation procedure is performed as plus input keys, hashing that, and O plus ciphertext G with probability half. So this procedure does not leak the information of the input. This scheme is almost secure, but the remaining problem is that choice bit of another case should be kept secret. For example, B0 is distributed uniformly random, but the joint distribution of B0 and 1 minus B0 is not uniformly random. So we have to hide another case of the choice bit of another case. To solve this problem is very easy. Just garbling B0 and B1 by classical technique that is introduced in the first slide. Classical garbling schemes required 4 ciphertext, but each of them is not k-bit but 2-bit because each ciphertext contains bi and permute bit that is used for the permute of 4 ciphertext. So then the resultant garbling algorithm for single AND gate is the first is set input keys and permute bit as this. One key is 0 key plus D and choose the permute bit. And then define the case output keys by using the choice bit B0 and B1. And finally encrypt B0 and B1 and next permute bit by using the classical garbling schemes. These garbling schemes finally output all keys and ciphertext, 5 ciphertext. But k-bit element is only the first element, and B0 C gamma, B1 C gamma, and B2 C gamma, B3 C gamma is all 2-bit ciphertext. So this garbling scheme contradicts the lower bound. Okay, next we explain the case of garbling multiple gates and other types, for example, or NAND or something. Let's consider this circuit. For input AND gate, input AND gate means that one of input one of input wire of the gate is also the input wire of the circuit. If so, we can choose the difference D and apply our technique as a single AND gate. So 1 kbit ciphertext per input AND gate. So it requires this number means that the number of kbit ciphertext. And for the other gate, we call mid AND gate. We cannot choose difference D because D is already defined as a difference of the output keys. So we have to adjust the difference to different one to the other using another ciphertext E. So for mid gate requires a 2 kbit ciphertext. ASIACRYPT or an XOR NAND and other standard gates can be garbled in a similar way. And if the garbling an XOR gate, we can further reduce the ciphertext by using the free XOR technique. The result is no ciphertext per input XOR gate and single kbit ciphertext per mid XOR gate. Security is only for this slide. Our scheme achieves a simulation-based privacy that is defined by Berare, Huang, Logaway. In the paper, we prove the security in the random walk model. Actually, our scheme may be proved by assuming a variant of correlation robustness, but this assumption is very complicated and very artificial, so we prove the security only in the random walk model. So the final is efficiency comparison. The first is comparison in plane setting. In plane setting means that the topology of circuit is public and the type of gate is also public. In this case, the most efficient scheme is half-gated scheme. This requires 0 kbit ciphertext in XOR gate and 2 ciphertext in AND gate. For simplicity, we consider the gates that consist of AND gates or XOR gates, 2 types of gates. If so, in half-gate scheme, you cost 0 ciphertext XOR and 2 ciphertext for per AND gates, and totally 2 times k times the number of AND gate. And in this work, 0 or 1 kbit ciphertext for XOR, and 1 or 2 ciphertext per AND gate. And finally, we obtain the total bits of garbled circuit is here. The left side is means that 2-bit part of our garbling schemes. And the right side is a k-bit part, and 1 kbit element is required for the input AND gate, and 2 ciphertext is required for mid AND gates, and 1 kbit element is required mid XOR gate. So comparing this result, our scheme is more efficient than half gates if this equation is held. But this equation in semi-private function setting, semi-private function means that the topology of the circuit is public, but the type of gate, it means XOR or AND or NOR or something, is private. In this setting, the most efficient scheme, the most efficient known scheme is GRR3. This requires totally 3 times k times the number of gates. And this work costs this one. That is always good better than the GRR3. So the SPF setting, our scheme is the most efficient scheme. And we note that for theoretical sense, our scheme cannot garble an identity gate. Identity gate means that pass through the one of input. Such circuit is meaningless, but classical scheme as a GRR3 scheme can garble such gates. This is a summary of result. We show a garbling scheme that circumvents the lower bound. Garble down the gate contains less than 2k bit, but instead contains additional 4 2-bit ciphertext per AND gate. And efficiency depends on the structure of circuit. And in plain setting, half-gate scheme may still be the most efficient scheme. And in SPF setting, ours is the most efficient scheme. Thank you for listening.
So any comment or question?
Quick question. Is it possible to have like garbling, but using both representations for different part of the circuit? So for example, you have a part of the circuit that has a lot of AND gates. You switch to your representation, and then once you get to a part that requires more XOR, then you switch to the half-gate approach, which has, could this approach work?
At least now, I have no idea. So half-gate scheme is very complicated and optimized to use free XOR techniques. So it's difficult, I think.
Well, I mean that you're outputting labels at some point, and then those labels, you now use them for the half-gate approach instead. For now, I don't sure, sorry. Okay, thank you.
Do you have any ideas on how to sort of restore the free XOR freeness? Like for XOR is in the middle of the circuit. Because that would kind of make your scheme a winner unequivocally, right?
Sorry?
So right now in your scheme, the XOR gates are only free if they're at the inputs. Do you have any ideas on how to make them free everywhere?
For now, I don't have an idea. Sorry.
That's fine.
I think it is difficult because difference is automatically defined as a difference of the output keys. The output keys is distributed uniformly random. So I cannot control the difference for now.
Okay, any other questions, comments? Okay, let's thanks to Real again. So the next talk will be about constant Brown asynchronous multi-party computation based on one-way functions by Sandro Coretti, Juan Garay, and Martin Hurt, and Vasilis Sikas, and Juan will give a talk.
Thank you. Hello, everybody. So this is constant Brown asynchronous multi-party computation based on one-way functions. Joint work with Sandro Coretti, Martin Hurt, Vasilis Sikas, and I just noticed that Vasilis' name is in smaller font. You see that? That's not done on purpose, and I hope Vasilis is not watching. but he cannot do anything about it, so we'll continue. All right, so secure multiparty computation, we already saw some definitions. We are talking about mutually distrustful parties trying to compute a function of their inputs. And the idea, security-wise, is that this computation should emulate the situation when we have a trusted party performing the computation for the parties. Okay? That's what we call these days the simulation-based paradigm, where you would have this ideal world here with the trusted party doing the computation, and the real world where the protocol is being run. And a distinguisher could not figure out, which world the computation is happening. So it's called the simulation-based paradigm. And in fact, is more than that. Is the universally composable in the sense that then if you have this security definition, you can have this ideal functionality. Okay, and any protocol realizes functionality can be plugged in other protocols, and those protocols can be running concurrently in very complex environments. All right. So that's a UC framework, simulation-based security. And typically, all these protocols are designed and analyzed in what we call a synchronous communication network. Okay, where each party is connected by secure channels, and this is an assumption that we're going to be making now for simplicity, but typically you would just need reliable and authentic channels, and you can do security, you can implement the secure aspect if you are in the computational setting. So in this synchronous communication network setting, the protocol proceeds in rounds, and messages sent in one round are guaranteed to arrive in the next round. Okay? So that was the synchronous setting. We mentioned UC. Turns out that this plain UC framework is inherently asynchronous. Okay, in the sense that the adversary has full control of a message delivery between even between honest parties. And there is in fact, there is a synchronous version of UC, okay, introduced by Katz, Maurer, Tachman, and Zikas, okay, which makes the UC framework synchronous and therefore easier to, design protocols for and analyze security and so forth. Okay, so because synchronous network is great for analysis, and how would you implement this in practice? It would be, you would assume that participants has more or less synchronized clocks, and there is a time bound on the message latency. Okay, and then you would have a round, but typically this round, this upper bound on the latency would be higher than the average transmission time, so that's one drawback. On the other hand, we mentioned the UC framework, which is totally asynchronous and overly pessimistic. And in fact, there might not be a reason for that, because just give you this quote from the blockchain era that says, if information is it diffuses, it's easy to spread and hard to stifle. And anybody knows who said this? Blockchain era. All right. So this to motivate that, you see the asynchronous network is overly pessimistic. Okay, so in fact, what we would shoot for, and this what we're doing in this work, is that messages, this network is asynchronous. There is no synchronicity assumption, but messages get delivered eventually. Okay, so in this network, the adversary may delay messages by an arbitrary, by finite amount of time. It might be able to reorder messages, Okay, but there's no deletions. Things are, eventually going to get through. Okay, and in fact, this is the model that was typically considered in early works in fault-tolerant distributed computing. Okay, you might be familiar with this famous impossibility result by Fisher, Lynch, and Patterson. Okay, and in fact, in asynchronous MPC by Menard et al. Okay, so in this sense, this asynchronous network with eventual delivery is opportunistic because you're not going to wait for the maximum, delay to move to the next round, but things are going to, as soon as they can, the message will arrive. And in fact, we noticed that this type of network, this capability had not been modeled in UC. Okay, which is one of the things we do. This is not our main result, but we need this tool to be able to say formally what we achieve. Okay, so we formalize one contribution is we formalize this asynchronous model with eventual delivery in UC framework. For this, we need the notion of asynchronous run complexity. And also, we have to model what the basic communication resources in this framework will be, and those are a secure channel. As I say, instead of secure channel in computational setting, you can think of reliable and authentic channels. And a broadcast type functionality, which is asynchronous Byzantine agreement. Okay, and it's worth pointing out here that in the synchronous setting, you would typically assume a broadcast functionality, right? You have like point-to-point communication, and you have broadcast functionality. Turns out that in this world, broadcast is not achievable. Okay, essentially, if you have a distinguished sender, you cannot wait for that sender because you don't know if the guy is late or is being delayed. But what is achievable is the Byzantine agreement. Everybody has an input version of the problem. Okay? And this is the broadcast-like communication resource for this type of network, for this type of setting. Okay, so once we have we have done the modeling for this asynchronous model with eventual delivery, we come to our main result, which is a constant round MPC secure multiparty computation protocol. And by constant round, we mean that the run complexity is independent of the circuit's multiplicative depth, is based on standard assumptions, PRFs, tolerates up to a third of corruptions, and it turns out that this is optimal in this asynchronous setting. And it also tolerates an adaptive adversary, which means that adversaries may corrupt parties. They don't have to commit to which parties to corrupt at the beginning of execution, but it's a dynamic type corruption situation. Okay, so those are the two things that we do. So let's see what the situation was before this. Prior work on constant round MPC protocols in the synchronous network. We have a bunch based on circuit garbling, as we just saw. We have more based on FHE. This is due to Asharov et al. And in this setting, you can tolerate up to a half of corruptions. Okay, and here, you also have to assume, remember I said in synchronous networks, broadcast works. But if you want to do it constant round on a point-to-point setting, there's, you have to settle for expected constant round, okay, for these primitives. I mean, you can assume it as a resource, and it will be just invocation and broadcast is one round, but if you want to implement it in a point-to-point network, that is expected constant. And this was noticed early on, in particular we had a paper in crypto formalizing this aspect. Okay, but the bottom line is that in the synchronous world, So constant round MPC protocols existed, as opposed to in the asynchronous model with eventual delivery, our model. Until this concurrent and independent work by Rand Cohen in this past PKC, which shows how to do asynchronous MPC based on FAG. Okay, and in fact, that's why our paper now is called based on one-way functions, because Rand already showed how to do it based on this stronger assumption. This protocol tolerates n/3 corruptions, which we said is optimal, but is secure against static adversaries, and also as ours assumes this resource asynchronous Byzantine agreement. Okay, so this was the situation so far, and there are other known protocols, but for asynchronous MPC. Okay, but the run complexity was proportional to the depth of the circuit. Okay, so until this result, after this year, there was a gap between synchronous and asynchronous. Okay, so let me, tell you a little bit about how we formalize this eventual delivery capability in the UC framework. So one first resource is what we call the asynchronous secure channel. Okay, and here you have a sender, a receiver. Okay, and the secure channel functionality stores messages and maintains some delay. Okay, this is a fixed integer. Okay, that the adversary is going to be able to manipulate. Okay, the adversary is going to be able to tell. This is intuitively this is T, so the delay in the number of operations that this functionality is going to wait until delivering a message. Okay, and these things work in a fetch mode. Okay, if you are supposed to receive a message, according to the protocol, you're going to keep asking the functionality, do I have a message? Do I have a message? All right? The adversary can manipulate that, but up to T, because then polynomial time adversary is going to be running out of time. Okay, so this is how we model asynchronous secure channels. All right, and then we can formulate the notion of protocol execution in this model, where the party is going to be sending messages using this resource and then polling for messages. Okay, so naturally you can now define the notion of round complexity in this setting as the number of times, the maximum number of times that the protocol switches between sending and fetching. Okay, that's the natural notion, round complexity for asynchronous MPC. So that was a secure channel. Similarly, we can talk about asynchronous secure function evaluation. Okay, where the functionality is going to collect all the inputs, all right, and then as when the computation is performed, everybody provide inputs. Then the adversary might be able to influence it. Well, I'm going to increase the delay, or reduce the delay, but it cannot do it, arbitrarily because it's going to be running out of time. Okay, and importantly, in this setting, there is no input completeness in the sense that not all honest parties are going to be able to provide inputs, because you cannot wait for some of them. You won't be able to distinguish if some party is late or is corrupt. Okay, but you can agree on a core set of parties that are going to be providing this input. Okay, that's fixed, and that's a computation that's going to be performed. The other parties are going to be assigned a default value. Okay, this is different from the synchronous setting where all the honest parties' inputs are going to be taken into account. Okay, and similarly, we mentioned asynchronous Byzantine agreement as a resource. It shares the same profile with asynchronous SFE in the sense that it's going to be collecting inputs. Okay, and if all the inputs are the same of this core set, that's going to be the outcome of this broadcast-like functionality. And if the inputs of the honest parties differ, it's going to provide some value provided by the adversary. Okay, but it's going to be consistent. Everybody's going to see the same value. Okay, so we model the communication resources for asynchronous MPC. Now we're going to go to, we're going to see how to build a constant round asynchronous MPC protocol. Constant round means the run complexity is independent of the circuit's depth, based on standard assumptions, as I said, tolerates a third number of corruption, is unsecured against an adaptive adversary, which I'm repeating here. Okay, and the function, we're going to be assuming that is specified by a Boolean circuit. And protocol overview, the protocol is going to consist of 3 phases. In one phase, we're going to be computing, in the first phase, a distributed version of a garbled circuit, as we just saw, or a variant of it. Okay, but the sort of pre-computation, this garbling phase, it's going to be a constant depth function. Okay, this is basically said, well, we're going to garble things, we're going to be generating randomness. Okay, this can be done in constant time, constant number of rounds. And for this, we're going to be using a protocol by Benor, Kelman, and Rabin, which, if you're familiar with the literature, is an unconditional, it's an information theoretic secure protocol for asynchronous networks, models. Okay, but same as, so this is the asynchronous version of BGW, the information theoretic MPC protocol, and as such, the number of rounds is linear in the depth of the circuit. Okay, so that's one thing, except that for this pre-computation phase, because this function is constant depth, we don't care, it's still going to be constant. Okay, so that's one thing. The other thing is, if you're familiar with this protocol, these protocols work on arithmetic circuits. And I said we're going to be working on Boolean circuit representations of functions. So we're going to have to do some tricks to adapt this protocol to our setting. After running this, we're going to be at phase 2, where players are going to be complete this phase, circuit garbling. And finally, in phase 3, parties are going to be computing this garbled circuit locally. Okay, so we said Boolean circuits, circuit garbling. And let me remind you a little bit what this is. So we have this Boolean circuit representing the function, and for each wire, we're going to have a mask, a bit MW, and 2 keys, depending on the value of that bit. And then every circuit is going to be evaluated, maintaining the invariant that if the mask value is Z, then one key is going to be known, and the other key is going to remain secret. Okay, this is a traditional version, variant of the traditional garbled circuit approach. And this can represent it like this for a generic gate. These are going to be the mask values. Okay. Oh, and we're going to be using a circuit that is usually only uses NAND gates. NAND is a complete gate, so you can just do all the, just use NAND gates. So here, for each value, each mask input values, what we're going to be doing is first unmask the inputs, perform the computation, and mask them again. Okay, and then the garble entry is going to be the encryption, double encryption using the 2 corresponding keys of the mask output and the key corresponding to that wire. Okay, I'm simplifying notation here using Z for all the outputs, but it would be corresponding to each row. Okay, and that's pretty much what I'm saying here. Okay, and so A and B are the 2 input wires to the gate, and C is the output wire. Okay, so it's the basic Yao circuit garbling approach. Now, I mentioned that we were using this big BKR MPC protocol to do things, right? So one might wonder, well, you can do this, you can probably do the, encryption, evaluate the cipher using the same protocol. So one issue is that, well, that's going to be a huge circuit, not necessarily constant. And the other issue is it will not be black box. Okay, so what we use is a distributed encryption approach due to formalized by Damgard and Ishai, which, if this is the regular encryption formulation, distributed encryption is as follows. Instead of just one key, assume n keys, one for each party. If you're trying to encrypt a message M, you seek a share M, and then give that share to the ith party, who is going to encrypt it and send it to everybody. Now, assuming everybody has, at some point, all the keys, okay, they're going to be able to decrypt and make sure that reconstruct the secret sharing, and that would be the outcome. Okay, so this was circuit garbling with distributing encryption. So before, remember, we saw for each wire we had 2 keys. Now we're going to have 2 key sets for each wire, 1 key for each participant. And the invariant is going to be similar, that if the mask value is Z, then one set is going to be known, one set of keys is going to be known, and the other one is going to remain secret. Okay, so this was garbling without distributed encryption, and this is with distributed encryption, which is similar, except that here, what we represent by this, the secret sharing of the outcome and the corresponding sets of keys. Okay? So this is going to be done by this BKR protocol that I mentioned. All the shares are going to be sent during this pre-processing for each gate, for each table, to all the parties. And all that process is a constant depth function. Okay, so this is the BKR protocol that's going to be choosing mask and subkeys. It's going to be computing this secret sharing of all the tables, and it's going to giving the parties their right shares of things. Okay. Now, so there are a couple of things that we have to take care about here. One is that, well, I mentioned we are going to be using this protocol to do the evaluation. This is linear depth, but this is a constant depth circuit function. And the trickier one is that we are talking about a Boolean circuit, and this BKR protocol is for arithmetic circuits. So we have to make sure that we can compute arithmetic circuit is a NAND operation. This is easily done by having this arithmetic operation in the circuit, except that now you have to make sure that all the inputs are 1 or 0, right? And there's another technique we can use to make sure that corrupt parties don't deviate from that all values that are input are ones and zeros. And there is another technique, another technique to achieve this. And if that when you do that in the beginning, and if the party doesn't do that, you just replace his input value by a sharing of 0. All right, so I'm out of time almost. Okay, so we do all the sharing, and then parties start encrypting, with their own keys, with their own shares of keys, shares of the values they have and send to everybody. Okay, and remember, in the output table, we have shares of keys that are needed for the next wire. Okay, so thing diffuse percolate through the circuit. Okay. Now, once all that happened, players are able to compute to evaluate this function, locally, given that they were able to reconstruct all the keys from all parties and all the shares. Okay, so this why does one encrypt things and not just secret shares? The reason is you just send stuff that can be decrypted that opens up just one row of the table. Okay, so and you wait until you have enough shares that are T-consistent, lie on the right polynomial. Okay, just to recap, we presented a protocol, constant round protocol based on one-way functions. One-way functions because this encryption is based on the only operation that we have here is encryption that can be based on one-way functions. It's computational secure against adaptive adversaries, optimal order players, constant round, and it's a black box on one-way functions. And the full version is in the ePrint. And that's it. Thanks.
So we have time for one quick question. So if not, thank you, Juan again. So the next talk will be the last talk of this session and the conference. It's about reactive garbling schemes by Jesper Nielsen and Samuel Lanicelli. And Samuel will give a talk.
Yes, thank you very much for staying for the last talk. This is joint work with Jesper Nielsen, and I'm going to talk about reactive garbling schemes. So in this presentation, I'm going to talk about our result. And our result is three main things. First, we define reactive garbling schemes. And then what we can show is that using reactive garbling schemes, we get reactive two-party computation from reactive garbling schemes, and it's black box against a malicious adversary. Now, one thing to note is that previous protocols for 2PC don't actually use garbling schemes in a black box manner. They actually have to use white box details about the garbling scheme to actually get security. And then, of course, we have a result that we can construct reactive garbling schemes in the random oracle model, but for this presentation, I'm not going to go into that. So what is reactive computation? So first we have, initially we have a state which is just 0. So we have a state, and we have a round which will start at round number 1. And then at each round, so at round I, the first player inputs a function and an input x. The second player puts in an input y, and then the functionality has an output z and some v, which is sort of going to be added to the internal states, which it computes from f, x, y, and the current state. Then it's going to actually update the state for the next round, and then it's going to output both the output value z and the function to P2. So this is reactive 2PC. And so now we're going to talk about what a garbling scheme is, first of all. So we can do a quick recap of what that is. I already assumed some familiarity, so this is just a reminder. So what do garbling schemes achieve? Well, this comes from basically it's saying, okay, we had a construction called Yau's garble circuit, and it achieved something. But this something was never formally specified in the original paper. So Bellari, Huang, and Rogway came up with a definition of garbling schemes which showed what garble circuits realized. So now the next question which comes to mind is why do we even why did they define a garbling scheme? Well, there's two principal reasons. So first of all, if you have a protocol that uses a primitive in a black box fashion, well, that protocol is more likely to be secure, because then you don't have to care about the implementation details under. And the other thing is also you can, because of this, you can easily say, okay, this implementation is better in this case, and this implementation of this primitive is better in this case, and then you can choose without having to worry too much about security. So there's many applications of garbling schemes: secure outsourcing, secure computation, private function evaluation. There's many more, KDM security, for example, and it's a very important. So just to remind you quickly what a garbling scheme is. So this is what would be completely insecure protocol for garbling. So initially you send the sender sends a function f to the receiver, and then later on he sends the input x to the receiver, and the receiver sends the output. Now, what we actually want from a garbling scheme is three properties typically. First of all is correctness, that it gives the right output, but we also either want privacy, which means given the garbling, what we garbled, the receiver shouldn't learn the function or the input, and then obliviousness hides the function, the input, and the output. So these are properties. Okay. So global view of garbling schemes. This is how a garbling scheme typically works. First, you garble the functions. This gives you an encoded function, an input encoding string so that you can encode some inputs, and a decoding string which allows you to actually decode an output. And this is the description of function f, and this is the security parameter written in unary. So then the next step is you encode the input. So you take the input encoding string, you take an input, and it gives you an encoded output. Then the next step is blind evaluation, where, for example, the second player can take the encoded function and the encoded input and produce the encoded output. And then finally, you can extract the output using the decoding string and the encoded output. So this hides the output, this hides the input, and this hides the function. So why did we define reactive garbling scheme? Well, there's certain things that reactive garbling schemes can't do. First of all, as you saw in the previous diagram, there's no partial input and output defined. And sometimes it's useful, for example, in secure outsourcing, to be able to provide partial input. You can't assemble garbled functions together, so you might want to garble one function and then another and decide, oh, I want to apply F and then G, or vice versa. For example, in signal processing, you might want to do a certain amount of operations in certain orders depending on the data. And you can't do black box constructions of 2PC from garbling schemes. This is something that was one of the original goals that Rogway wanted to do, that we build things black box from garbling schemes, but we can't. There are certain details that, something that was missing, and reactive garbling schemes give that. And then we also want to reuse encoded outputs, so we can get an encoded output and then feed it into another garbled function. So this is what reactive garbling schemes allow us to do that garbling schemes can't. So how do we actually get a reactive garbling scheme? So basically what we do is we take garbling scheme and sort of expand the definition. So we're going to do a couple of things. First of all, we'll vectorize. So this means that instead of having one input, we'll have a vector of inputs. And the same thing for outputs, we'll have a vector of outputs. Then we'll have output encoding strings, so ways that we can say how outputs are actually encoded. And this will allow us to do things. Then we have tags, which is, we need a way of saying which functions we garble and what they garble to. So tags are sort of identifiers or names of functions. Then we have a linking algorithm, which says how we can combine two garbled functions together, link them together. And then, of course, we need a new notion of security called confidentiality, which is, yeah. So vectorizing garbling schemes is very simple. So instead of having encoding a symbol input, you can encode a vector of inputs. So you have an encoding for each of the values, and then you have decoding for output. So you can decode partial outputs. You can encode partial outputs. So and decode. So basically everything is vectorized. So you can decode partial input, decode partial output. You don't need to wait till everything is defined. Yeah. So the evaluation takes partial input, partial encoded input, and gets out partial encoded output. So what's an output encoding string? Well, it just maps an output value to an encoded output. So it's very similar to the input encoding, and it's going to be useful to link two garblings. So this is one of the key things in the reactive garbling scheme is a linking algorithm. So what it does is it takes the output encoding string of one function and the input encoding string of another function. So this is like the function we're converting the output, and this is the one we're sort of linking in. And basically, it gives us something called the linking information, which basically what it allows us to do is takes an encoded output and to convert it into an encoded input for another garbled function. So then, of course, to describe which functions, so we know, oh, we're garbling this function, and when we're linking this function to this other functions, well, we added tags. And so the garbling scheme takes an additional parameter, which is a tag, which sort of names the function. Now the garbled function has a tag, the input encodings have tags, and the same thing for the encodings, and then in addition, there's a linking algorithm. So the linking algorithm takes the output encoding string. So this is saying how the output of a function is encoded, and takes the input encoded of another function and then links them together. So now you can take the encoded output of one function and turn it into the encoded input for another function, garbled function. So then we have the evaluation procedure. It takes a set of garbled functions, a set of garbled inputs, and a set of linking information, and then based on that, it actually just computes the encoded output. So the definitions are fairly simple extension of garbling schemes. And then so obliviousness and privacy stay the same. So you basically either hide the function or the output, or you just hide the function and the input, but then you have to worry about confidentiality. We extended basically some outputs that are encoded. You can only learn what their value is if you have a decoding for that partial output. And this allows us, this notion of confidentiality is actually implies both obliviousness and privacy. Because if you have no decoding information whatsoever, then you're back to obliviousness. And if you have all the decoding information, then you get back privacy. So this implies this and this. So toy example, just to see how it kind of looks like. Well, you could garble F and garble G. So just you end up with two garblings. Then you can link G to F. So this is all it's doing. It's basically linking, so it looks really nice. And then you can provide encoded input, and then you can decode the output, and basically you end up with something that looks like this. So visually, it's very nice. So what are the applications of reactive garbling schemes? Well, you have reactive two-party computation. It's a black box. So it only relies on reactive garbling schemes and not on its implementations. And it's going to use the watch list. And we also have Lindell's cheater detection. So this was a technique that Lindell used to reduce the number of circuits you need to communicate by having a phase where the second player, if he learns that the first player cheated, he's able to extract his input. And we can model this using reactive garbling schemes, and again, it's in a black box fashion. And then we can also look at mini Lego as a type of reactive garbling schemes, because mini Lego sort of, this soldering is actually, in our language, is actually this linking garbled functions together. So I'm going to actually go in a little bit more detail about how you can realize the reactive two-party computation. So the idea is we're going to have a watch list set up. So the idea is that we're going to have many garbled circuits, and we're going to use half to verify that the first player is acting honestly. So this is basically making sure, okay, he's garbling the right function. And then we're going to use the other half for evaluation. And the way we're going to do this is we're going to evaluate all of them in parallel, and then the second player is going to evaluate them and then take the majority output as the result. The key is that what we need to do is get the majority have the correct output, therefore you get the correct output. Unfortunately, usually there's two main security issues that we have to worry about when we're doing two PC protocols. The first one is input consistency of the first player. So one thing that you can have is when you have all these evaluations that are taking place in parallel, but it might be that the player P1 who garbled the circuits is sending different inputs to each one. So you need a way to verify that he's using the same input. And the second thing is the selective failure problem. And this one is the problem that depending on the input of the second player, the protocol might abort or not. And this is a problem that we have to prevent, otherwise it leaks one bit of information. So how we enforce input consistency? Well, we're going to use a special verification function. And the verification function, this is for the forcing that the first player uses consistent input, is that the function is going to take the input of the first player as well as a mask for the first player. This is going to be used to hide his input. And it's going to take a universal hash function from the second player. And the idea is that this value, if the first player tries to use different x and x prime, this value is going to differ between the different evaluations, and the second player is going to be able to abort if the first player uses inconsistent output because of this property is that if x is different than x prime, then it's unlikely that the first player chooses an x prime such that this equation holds. So this is sort of going to do this. So how are we going to do this using linking? Well, it's very simple. First, we're just going to garble the verification function. He's going to send input x and k. The first player is going to send input x and k to the v. This is, of course, going to be encoded. The second player is going to choose g at random and going to send into the function. Now, he's going to get the output, and this is going to ensure that if for all the parallel evaluations they're the same, then except with negligible probability, then he used consistent input. And then we're going to actually link this function to the function we want to evaluate, and this ensures that we end up with an encoded input that's consistent for the sender. And to verify that this is all done, it's going to be enforced by the watch list. So it's very nice imagery. Now, selective failure attacks. Now, how do we prevent? So we want to avoid that whatever or not the P2 aborts depends on his input. So how are we going to do this? Well, the idea is that we're going to garble an identity function. So this is going to, and the P2 is actually going to choose a random input. And so this is going to be uncorrelated with his actual input at this stage. So this is random. And then what we're going to do is we're going to actually use privacy amplification. So the P2 is actually going to select a function h such that h of y prime is actually equal to y. So in this way, he's going to use privacy amplification to hide his actual output, and so that even if there is an attempt at a selective failure attack, well, the probability that it's going to abort is going to be independent of the receiver's output because we do this. And then, of course, we just link everything together. So then this creates an encoded y prime, which because of the linking gets fed to the hash functions, and it gives an encoded output y. And then this is fed to the functions we actually want to evaluate. So just this linking allows us to prevent selective failure attacks. And both of these things, input consistency and preventing selective failure attacks, have previously been done by using white box modifications. And it's most likely that it depends intrinsically on the properties of the garbled circuits. And you have to be careful because depending on your instantiation, it might not work. So this, if you have a reactive garbling scheme, our protocol works. And in summary, we extend garbling schemes, and then we can securely realize reactive 2PC from reactive garbling schemes in a black box manner, and we actually have an instantiation. Thank you for listening. Thank you for staying for the last talk, and I'm happy to take any questions. Thank you.
So any questions, comments?
So if you had this notion of reusable garbled circuits, if you added like some linking capability and saving state, that would, no? Yeah, pass state to the next evaluation.
Any other comments or questions?
I have very basic question. Sorry if it is known by everyone. Why do you need to hide a function f?
Maybe one more question, comment. Okay, if not, let's thank to Simel again. So that's the end of the session and the conference. Maybe he will have some word, maybe?
So thank you very much, all of you. I hope that you enjoy the conference, and I hope you will have a good trip back, and see you next time. Thank you.